Okay, so dividing radicals. So one thing you're going to see is we're going to take the nth root of a over b. So if n is even, then a over b must be greater than or equal to 0. I mean, we could take the nth root of 0, which is always 0, but if it's even, it has to be 0 or positive, right? We can't have a negative root. So either a is positive and b is positive, or both a and b would have to be negative. So just the quotient will be and if n is odd, then it doesn't matter, right? then b can't be 0. All right, so everybody's greater than now just throw in here b. Either way, b can't be 0, right? We can't have a 0 in the denominator of an expression. So in its simplest form, if we do stuff like maybe we start with something like root 10 divided by root 5. So if we have a quotient with individual radicals, we can combine them underneath one radical sign, right? We can take the radical or the root of the quotient. So the root of 10 over 5, which is root 2. So you can skip that middle step, right? You can just say root 10 divided by root 5 is root 2, right? 5 goes into 10 twice. What else do we have? Something like, let's do like 4 root 14 over 8 root 2. So if we have numbers outside the radicals, so kind of the same idea as in multiplying. We would multiply the numbers outside the radicals. In this case, we divide the numbers outside the radicals. Okay, so we would treat this as 4 over 8 times root 14 over root 2. Okay, which would be equal to 1/2 the 4 over 8 and the root of 14 over 2. So 1/2 root 7. Right? Excuse me, which then becomes root 7 over 2. Excuse me. Yeah, well, not much I can do about it. Okay, so 4 over 8, so you deal with the numbers outside, you deal with the numbers inside, putting them under the same radical sign, simplifying, and ending up with root 7 over 2. What if we have a higher index, right? What if we're not doing a square root, but we're doing a cube root? So the cube root of 3/8. So in this case, it's already together underneath, but in this case, 3 and 8 don't reduce, right? 3 doesn't go into 8, there's no common factor that can be divided out. So in this case, what we're going to do is we'll write this as the cube root of 3 over the cube root of 8, because the cube root of 8 is 2. So this simply becomes cube root 3 over 2. And remember your index, right? So when you're doing these problems, when you get the test, cube root, just make sure you're always writing the 3 for the index, or 4th root, that you don't leave the index off anywhere, right? And check over at the end of the test, make sure that that you've handled that. Okay, let's see. What do we do with something like root 6? Well, let's put it together. So we get the root of 6 over 5. So again, we can't simplify the 6/5, right? You're not going to write that as 1 1/5 or anything. You're going to leave it as 6 over 5. So what we're going to do is we're going to split it out as root 6 over root 5. And one of the things when we do division with radicals is that we do what's called rationalizing the denominator, which is changing the denominator to a rational number, right? In other words, we're not allowed to have radicals in the denominator, right, when we're simplifying. So the way that we do this is Well, what can we do? We can multiply root 5 by root 5 and turn it into a 5. So we say, okay, I'm going to multiply the bottom by the root to make that root 25, or 5, right? Root 5 times root 5. What do I have to put up here then if I want to maintain this equal? Also a root 5, right? So what's root 5 divided by root 5? 1, right? So we're just multiplying by 1. It's just a special form of 1. So up top, 6 times 5 is 30, and on the bottom, root 5 times root 5 is 5. Okay? So in this case, we have a rational denominator. Right? So we can never have a radical in the denominator. And the process is called rationalizing the denominator. That works regardless of, I'll give you a moment, regardless of whether the denominator is a number or the denominator could be a variable. So we could have root 7 over x. Okay, so what do? We split it out. Root 7 over root x. How do I get rid of the root x? Multiply by root x over root x, right? So the idea is whatever square root we have on the bottom, that's what we're going to multiply by, but it has to be over itself, right? It's got to be as the number 1. So up top, root 7x. On the bottom, x. You don't get to do any canceling. Okay? You don't want to cancel here anyways, because we just put it in, so let's not just, turn around and take it out. And we can't cancel here because they're not the same. This is the square root of x, this is x. That's two totally different numbers, right? I mean, if x were 10, this would be the square root of 10, this would be 10. That would not cancel. There's no common factor there. And, let's try a, so let's do a cube root, and let's do 12x squared over 5y squared. So with the cube root, we're going to have a little slightly different thing, right? So here, what we wanted to get was the square root of x squared, which gets rid of the radical sign, right? So what we needed underneath the radical was a perfect square, right? Multiply root x times root x, you get root x squared. That's a perfect square. We take the root of it, we just get x. Here, we're going to need a perfect cube, right? So we're going to split it out. Like so. And now what we've got to figure out is, throw an equal sign in there because it's equal. So what am I going to multiply this by? So it's got to be a cube root, right? You can't multiply a square root times a cube root. I mean, if you do, you just write them beside each other as a product. So cube root. So I need to get the 5. I need 5 cubed, basically. Okay, so we've got 5. I want to get 5 cubed. I'm going to have to multiply by 5 squared, also known as 25. I need something I can take the cube root of. I've got y squared. So what do I need? I'm going to need a y here. So the 5 times the 25 will give me the cube root of 125, right, which has a cube root, right, 5. And we'll get y cubed, which has a cube root, which is y. So what do I have to put up top, though? Same thing. Cube root 25y. So really, we're just multiplying by 1, right? We're changing its form, but not its value, right? It still has the exact same value, but we're changing its form. And with this new form, we'll have a rationalized denominator. So up top, we still have a cube root. 12 times 25 is 300, yeah? X squared and y. Okay, so we're just taking the product of everything that's underneath the radical sign. Over, so it'll be the cube root of, well, let's write it down, it can't hurt. 125y cubed. So the top remains, right? It's just 300x squared y. And the bottom, the cube root of that is 5y. So we have a rational denominator, right? We've gotten rid of the radical. If it were a fourth power, we would have to multiply things that would give us a perfect fourth, right? Something that has a fourth root. Right? So you have to look at the number. If there's a 7 under there, you'd have to multiply by 7 cubed to give you 7 to the fourth, right? And then that would back off. At which point you might, instead of writing the numbers, you might just want to write it as a power, right? So I didn't really need to write 125. We could have written 5 cubed. And I could have written a 5 squared there. But we're dealing with small numbers, 5, 25, 125. That's not such a big deal. But if we start getting to 7, 8, 9, where you don't want to have 600, 256s or 512s floating around, then you might want to just say, okay, I got a 5, I'm going to multiply it by 5 squared. Okay, that'll give me 5 cubed. Okay, so just going back here, then what we could have written was 5 squared y, and down here 5 cubed y cubed. Okay, and that might actually make it a little bit easier, right? Because you can see, well, I need a power of 3. I've got 1, I put 2 on there, that gives me 5 cubed. Okay, I don't need the number because I'm just going to cube root it anyway, so the cube root of 5 cubed, 5. Right? And then the same thing with the variable. If that had been a y to the 4th, I'd multiply by y squared to give me y to the 6th, because it has a cube root, right? It needs to be divisible by 3. Basically divisible by the index. You need a power that's divisible by the index. Okay, questions on that stuff? All right, here, I'll give you one. Try this. Here's a 4th root. So 3, 4th root 11 over 4th root 2. Rationalize that denominator. And keeping the numbers reasonably small on purpose, right, so we don't get huge. Okay, so I've got a 2 to the 1. I need a 2 to the 4th. I need a 4th power and multiply by 2 cubed. If I put that on the bottom there, I got to put that on the top here. Okay, apparently I'm running out of power, so I'm just going to run down the hallway.
Still recording. Show them a pop on it. No, it's great. You're such a good person. No. How do you? Oh.
Okay, so now up top, 2 cubed. What's 2 cubed?
How did you get that numerator? 8.
Okay, so I'm just multiplying these two guys together.
What about the 3?
What 3?
The 3 at the Oh yeah. At the front.
Oh, right. What about the 3? We need that, don't we? Okay, so let's throw that back in. Okay, so we get 3 cube root, or 4th root, sorry, 88 over 2. All right, sorry, I forgot the 3. What about the 3? I left it off. Okay, so 2 cubed is 8, 11 times 8, 88. Question?
Do you want us to like here? Do you want us to simplify it? Like how? Or even here, do you want us to?
It's a cube root. Are there any cubes that go into 300?
Yeah, but do you want us to split it up and then do that whole thing that we were doing when we were multiplying?
Okay, are there any cubes that go into 300?
Yeah.
What? That's a square. Are there any cubes that go into 300? Yeah, so yes, you would have. If it would have, you would have. Okay, so the question was, do we simplify this further? And the answer is yes, but it doesn't, because there are no perfect cubes that go into 300, right? So would we simplify? Yeah, if that could be simplified, I would. But it can't be, because the cubes are 8, right? 8 doesn't go into 300. 3 cubed is 27, doesn't go in. 4 cubed is 64, doesn't go in. 5 cubed is 125, doesn't go in. 6 cubed is 216, that's way too big, right? So yeah, if that were like a 54 or something, then yeah, I would be splitting it out. I would have to, right? And then I would divide anything top to bottom if that happened. So if a factor came out of here that went into here, I would be simplifying.
Yeah.
And same here. If these could simplify, they don't. But, you know, if I pull the 2 and that was an even number, then, yeah, I would be simplifying. Is there a fourth that goes into 8? No, because you can see that it's an 11 and 3 2s, so there's no fourth that I can take. Okay, but yeah, definitely. We definitely simplify that if we could.
Mr. Hanover, I still don't get why you put the 2 if you cube the 2.
Okay, because I need a fourth power. The fourth root of 2 to the fourth is 2.
Why wouldn't you put it to the 4th?
If I put it to the fourth, then when I multiply these together, I'll get a 2 to the fifth, and that's too big. Okay.
Also 2 times 2 to the 3rd.
So what we're looking to do is end up on the bottom either with the square root of a perfect square, the cube root of a perfect cube, the fourth root of a perfect fourth, or whatever, the nth root of a perfect nth power, so that this can simply become a number. Okay? Anything else? Let's try one more. I'll give you a cube root here. We'll give you one. So how about 4 cube root 2? And then I'll just pause this and let you work. 7 cube root 25. So let's think about this as, let's rewrite this maybe as 4 cube root 2 over 7 cube root 5 squared. Okay, so recognizing, hey, we have a power of 5, which means then I want to multiply by cube root 5, which will give me a 5 cubed. And if I do that, I need to do that up here as well. So on, well, it just stays there. So on the top, we get 4 cube root 10, right? 2 times 5 is 10. On the bottom, we get 7 times, okay, let's just 5 really, right? 7 times 5. So 4 cube root 10 over 35. No canceling, right? It's 4, 35. Cube root 10 doesn't reduce, nothing goes, no perfect cubes go into that. Yep.
So basically what you should do is change like the 25 into
Change it into a power, yeah. Yeah, so if you can. If that was a 34, there's no, right? Then I would just multiply by 34 squared. And give me a 34 cubed down here, and I'd have a 34 squared, and I would work out the actual number then, like I did with the 88. Right, so multiply by 2 cubed. Okay, that's 8 now, and I get 88. Okay, anything else? Well, these ones, this is what they are.
This is what would be on the test.
No. What you want to do is you want to get to the conjugates. I know. Take me to the conjugates. Okay. Well, okay. You want a hard one? Here, we'll give you a hard one. Yep. Yep. Okay, so our first step is to say, hey, let's see if we can simplify this before we start trying to find perfect fourths, right? Otherwise, we're going to be multiplying this by an x, and that's already got a perfect fourth, and this by a z cubed and all that, but we can do reducing, right? So we can reduce the 18 and the 8. 2 goes into both of those, right? Into this 4 times and this 9 times. The 6 and the 10. 2 goes into both of those. So what I'm going to do is I'll just go here and we'll write out the new one, right? So it's 9, right? That'll be a 9 because the 2 goes in. Fourth root. 2 goes into 6 3 times. The x and the x cubed gives me an x squared up top. The y to the fourth is gone. It's going to cancel with the y to the sixth on the bottom. And the z is gone. It's going to cancel. Okay, so I guess we just get the 9 fourth root of 3x squared. Okay, our next one then is the 8 divided by 2 became a 4. Got a fourth root. the 10 divides by 2 becomes a 5. This x is already gone. It canceled into here. Y to the 4th, we're left with a y squared on the bottom, and we're left with a z squared on the bottom. So that's a much simpler expression, which we can then, say, well, what do we need now? We've got to start making perfect fourths. Okay, so let's just start with the 9. I'm just going to rewrite the original. 9, 3x squared. We don't much care about the numerator at this point. Fourth root, we got 5 y squared z squared. Okay, so on the bottom, I don't need a 4, right? I just need the root, right? I just need the root, because when the roots multiply together, that will get rid of the fourth root. So I need a fourth root. I need this to become 5 to the 4th. So what do I have to put inside here? 5 to the 3rd, right? 5 cubed. I need this to become y to the 4th. So what do I need in here? And I need this to be z to the 4th. Z squared.
Is it okay if I put 125?
Yeah. But remember, then you're going to have 625, and then it's going to become 5. Okay, if we do that on the bottom, we must do the same up top. So 5 cubed, y squared, z squared. All right, so what we're trying to figure out is, what do I need so that on the bottom I will have perfect fourths underneath the fourth root? Right, and it's only the denominator we do that for, and then we put this same term up in the numerator. Okay, so now we multiply. So I get 9 times the fourth root. So at this point, I can turn this into 125, right? 3 times 125 gives me 375. It won't have a fourth root, right? Because it consists of 3 5s and 1 3. There's no 4 of anything. Okay, the x squared just stays x squared, and we get a y squared, and we get a z squared. So that's what's going on up top. On the bottom, we get the 4. Right, and there's a 1 in front here, as 1, so we get 4. It's the fourth root of, so do you want me to write the fourth? We'll just take the fourth root of, right? So we've got to have 5 to the 4th, so it'll be 4 times 5. We're going to get y to the 4th, so there will be a y. We're going to get z to the 4th, so there will be a z. And we'll get 9 times the fourth root of 375, x squared, y squared, z squared, over 20 y z. Okay, and that is the full solution.
How does the 5 and the 5 cube just cancel?
The 5 and the 5 cubed become 5 to the 4th. And the fourth root of 5 to the 4th is just 5. Okay? So when you multiply these two together, instead of writing it as the fourth root of 5 to the 4th, y to the 4th, z to the 4th, we say, hey, we specifically made it so it was fourth root of things that had fourth power, so we'll just write it as 5y, z. Okay? Next. Binomial denominators. So you're going to get to bring in the conjugate now. Remember the conjugates we did yesterday? Oh, too bad. So binomial denominators. So we know how to handle a monomial denominator, right? If you have a radical in the denominator, you just multiply by the same, well, if it's a square root. Square roots are the easiest. If you have root 2, you multiply by root 2. Okay? With cube roots and fourth roots, it gets a little harder. You've got to multiply by something to give you a 2 or a 4. Most of the stuff that you're going to see will be square roots. Okay? Most of the stuff you'll see. So it's fairly straightforward. Binomial denominators, you'll only ever see square roots. So 6 plus root 3, let's say we have this, over 4 minus root 3. So first off, you can't cancel the root 3s. As tempting as you might like, it's just not true. Right? Because then you're saying, oh, that's the same as 6 over 4. Or if you're going to add 1, it's the same as 7 over 3. Right? If you're going to try and cancel it, it doesn't work. Remember, if you think something works, try it in your calculator. If it does work, Try it with a different number if it's a variable thing, and if it's not, then if it's just an expression like this, and you try it and say, well, okay, I think it's like 6 plus 1 over 4 minus 1, because I'm going to cancel the root 3's, you'll see it's not the same. Right? That's actually fairly obvious it's not, because root 3 isn't a 1, right? It's like 1.7 something. So you'll have decimals in there. All right, what we want to do is we multiply by, remember the conjugate? 4 plus root 3, right? That'll set up a difference of squares on the bottom. If I put 4 plus root 3 on the bottom, what do I have to put up top? The same. Yeah, same, right? Because I don't want to change its value. If I multiply, what is 4 plus root 3 over 4 plus root 3? That's 1, right? That top and bottom cancel. Okay? So on top, we're using FOIL, right? Distributive law FOIL, whatever you want to take, right? So we get 24. Okay, 6 times. If it helps, put brackets around it, make it kind of odds, right? So we get 24 plus 6 root 3. I'll just write out all 4. Plus 4 root 3. And what's root 3 times root 3? 3, right? So there's my 4 products. 24 plus 6 root 3 plus 4 root 3 plus 3. And what do we get on the bottom? Okay. So it's a difference of squares. If I multiply a plus b times a minus b, I get a squared minus b squared. So a squared is 4 times 4, 16, minus root 3 times root 3, 16 minus 3. All right, and now we can collect terms together. So up top, we get 24 plus 3 is 27, plus 10 root 3 over 13. Now, if the 13 went into the 27 and the 10, we would do some canceling. If there was a common factor that went into 27, 10, and 13, we would do some canceling, or we would simplify. Okay, in this case, not. You know, like, so if you look at it and say, oh, all the numbers are even, okay, then I can divide them all by 2. Right? If that had been a 28, and a 10, and a 14, we can divide everything by 2. So we basically, once we have this, we want to see, does it simplify? And the answer for this one is no, does not simplify, right? That is as simple as it gets. Okay, let me see, should we do one more? Let's do one more. It's got more roots and stuff like that. So, what shall we do? How about, what have we got in here? Anything exciting? Yeah, how about this? 6 root 7 minus 3 root 5 over 2 root 7 plus root 5. So that's my expression. If you're asked to simplify this, you're basically asked to rationalize the denominator, right? That's what we're saying, is you cannot have radicals in the denominator of any expression. So what do we multiply by? What goes on the bottom? 2 root 7 minus root 5. What goes up top? Same thing. 2 root 7 minus root 5. Okay? Because really, we want to multiply by 1. We don't want to change the value. Right? We're not changing this value. We're changing its form. Right? I mean, in the end, if you go 27 plus 10 root 3 and then divide that by 13, and you go 6 plus root 3 divided by 4 minus root 3, you'll get the same number, right? So that's a way that you can check your answer. If you have time, we only check at the end, but if you have time at the end and you changed this into a different form, you can work this out. Just go bracket 6 root 7 minus 3 root 5 bracket divided by bracket 2 root 7 plus root 5 bracket, hit enter, and then whatever we end up with down here, you do the same thing, and you should get the same decimal equivalent. Okay, let's do the top. So 6 root 7 times 2 root 7.
12 root 6.
Okay, so 6 times 2 is 12. Root 7 times root 7 is 7. 7 times 12 is 84. Okay? So we should know our first number, first term, right? Because we're multiplying root 7 like radicals. We're going to get just a number. Okay, what's our next one? Minus 6 root 35. Minus 6 root 35 again, right? 3 times 2. Plus 15. What do we get on the bottom? So 2 times 2 is 4. Root 7 times root 7 is 28. So we can write that. 28 minus 5. Okay, don't worry about the 2 root 35 plus, because the outer and the inner products cancel, right? We're only interested in 28 minus 5. You know, and we might as well write this, okay, as opposed to just going straight to 23, because you could just say, okay, this squared minus this squared. Okay, 28 minus 5, but you know, it doesn't hurt to write it, because we still have some simplification to do. So 84 plus 15 is 99, minus 12 root 35 over 23. Okay, 23 is prime, so there's nothing that goes into, but you know, if this had been a 21 or something, we could divide everything by 3. It isn't, it's prime, that's it, that's the answer. Root 35, there's nothing that comes out of that. There's no perfect squares that go into 35, right? But if there were, we would have to simplify this, right?
You need one that has some.
I don't know. I'd have to find one. I don't think I have any. I think you've got the idea. Easy. Shall I